Hello, this video is to have a brief description about part A1 of project number 2. I want to show you the modification you may need to implement in your solution. Here we have, I'm using the version number 4 of the API because I'm also using the data association helper function to show the student who may be using that one. So that one is offering version number 4 and not in the previous version. So I'm using initializing the API as before, and the rest of the program is very similar to what we had before, except that I remove some variables because now we are not implementing some of the modules, particular module D and E anymore. And then the rest of the things are very similar. I specify a data set and load that thing, and I get the pointer or handles to each of the function of the API I want to use. I add a new one here. I put this DA API, data association, so I'm using the API helper function. The rest is very similar. I remove some of the object here because I'm not showing certain things which did make sense in project 1, but not anymore in project number 2. I have created some buffers, yes, for the ground truth data samples, and also for the expected value from my Kalman filter, and also for the variance of the, more exactly, the diagonal element of the covariant metric. That is what I have. The rest is very similar to what we had before. There are no big difference. I create menus, the figures, Now I initialize in my program, and yes, I had to do some extra things that were not part of project number 1. I'm initializing this thing, suppose my Kalman filter. I'll put this here. Yes. Yep. Yeah. And this one should initialize my expected value and my covariant metric. Yes. I'm not doing much. I specify in here this argument telling which is the initial condition that I believe is the real one. And I'm sure about that because that is what we know from the dataset, that initial post is real, is correct. So in this case, I'm setting the expected value. It's here returning the expected value on the covariant. So I put this equal to the initial post, and I set the covariant to be plenty of zeros because I'm pretty sure that the initial expected value is the value of the state we are trying to estimate. So in that case, it's not the general case. I'm initializing with a covariant metric which is 0 for each of its elements. So I have full certainty. Good. I had to provide the statistical description, so I'm telling here that the standard deviation of the noise polluting the speed sensor measurement are 0.1 meter per second, and the standard deviation which corresponds to the gyroscope, which is in radian per second, but I specify this in degrees per second, so I put here and I specify this in radian per second, so I do know that both standard deviation. And also I specify the standard deviation of the range measurement. I specify here 20 centimeters. Yeah. And then I calculate these two matrices, which I need later. I will need this for my updates. That is the covariant metric of the noise polluting my measurement, the output of the system. And I also had this covariant metric describing statistical properties of the noise polluting the input of my system, which I used to call in that document that I released to you to read PU, talking about U, the input. In this case, I call the input BW. Okay, good. So I had this, everything that I needed to do initially, yeah. And the rest is very similar to what we had before. This is the event loop, if you remember. There are no big changes. Here, in this place at which we used to run the kinematic model for part A and for part E, we don't have that anymore, but we do have the prediction. Yeah, and the prediction, which is internally using the model, of course. The prediction, we need to provide this argument. We need to provide the current expected value and the current covariance. Yeah, we need to provide the inputs at this time, which are obtaining from measurement. And because my model is discrete time, I specify here the dt, and I also provide here the covariant metric describing the noises affecting my knowledge about the input. So this is the covariance of the noise polluting the speed and the angular rates measurement. Good, and that's it. I had also here the same that we had before. If we detect that delta t happen to be negative, or that means that someone is resetting the playback session. In that case, are going to reinitialize things. Okay, that is similar to what we had before, and then the rest is processing the LiDAR event. This is the LiDAR event, and the same thing that we used to do before, exactly the same thing. Of course, here when I need to convert from local to global and blah, blah, all the things that we used to do, I'm using my current expected value. Yeah. This is why I'm doing all this conversion from local to global using that expected pause on my platform. And the rest of the things are very similar, extracting the cluster, blah, blah, whatever was necessary there. So when I reach here, I already know after and running the data association as well here, I'm using my API function here, yes. And yes, and in that way, I'm in condition to get a set of objects of interest for which I do have association with certain landmarks, and that is the information I need to exploit. But because I'm pretending I have a sonar, I don't want to have this position in 2D of the object of interest in my local coordinate frame. I just want to exploit distance, pretending that I have a sonar, or pretending that it's like some sort of two-dimensional GPS for which I measure distance to satellites in place to be poles in our case. Okay, good. And then this is just doing that, pretend they are sonar, blah, blah, blah. So I get here the distance from the sensor to each, in this case from the 0, 0 of the car coordinate frame to the center of each of the objects of interest. This is what they have after data association. So these are already objects of interest for which I do know the landmark to which they do correspond, so that we do know this well now. So because I had that, now I'm in condition to run the updates. This is going to do all the updates. If I have 5 objects of interest, we are going to have a vector here with 5 measurement, 5 distances, okay? And then I'm providing for each of them, which is the landmark which corresponds. And I also am telling my update module, which is the covariance of the noise polluting those measurements. In this case, all of them have the same quality, so I use the same for everyone. Yeah, good. And if this update is going to process this, going to apply all these Bayesian dates through the Kalman filter, and it's going to return a new expected value and a new covariance. This is the posterior, and this is the prior PDF. So these parameters are describing a PDF which is Gaussian, so this corresponds to the prior, and it will be the posterior. Yeah. All right, and that's it. And after that, I'm doing the usual operation here. I'm recording things because I want to plot this at when the playback session ends. All these are the real-time plot, blah, 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 and nothing else. Okay, we'll run this program now. Yeah. I'm going to stop, yes, here. I'm using the same API that you are using, number 4, or number 3 at least for you, if you are not using the number 4 because you don't care about using the data association helper function. So this menu will be very similar. So I'm going to specify, in my case, this is part of my program, that is not the standard menu which we offer here. But suppose I say I want to specify here, according to the setting that I have in my program, this should have certain noise. I don't remember, I put here, suppose 12 centimeter noise affecting the range measurement, or the LiDAR scan for each of the ranges. The speed gain, we are not talking about changing anything here. This is the standard deviation of the Y Gaussian noise polluting the speed sensor. I will put here 10 centimeter per second, or this is in meter per second. And this is not about important. This is about the slowing down the playback. No worries, we don't need that. This is important. I will have to specify here that the gyro is being polluted by 3 degrees per second. Standard deviation. The noise is having is wide Gaussian noise again, of having a standard deviation of 3 degrees per second. All right, I don't expect to put any bias here, anything. I'm going to reset, so start from the beginning, and I run this thing. Yes, it's running okay. Yeah, we could see also, it's very interesting to see that, yes, data association is working well. Yeah, yeah. We come back. It's going to run all the way. Oh, you remember this well because this is exactly the same trip we apply and we process in project number 1. This is, I think, dataset 7. I don't remember now. Yeah, 7B. Yeah, and it's going to end. And this is very interesting because here we are showing we are analyzing the performance. What we have in blue here is the discrepancy for each of the components, x, y, and phi. I analyze the discrepancy between the expected value and the ground truth corresponding component. And I'm showing here also this envelope you have here, okay? Yeah, we correspond to 2 standard deviation. Here, this one is plus 2 standard deviation minus 2 standard deviation at each time. Because at each time, this estimation process is producing a Gaussian PDF that is describing our estimate about the state of the system at that time, and is providing that information through an expected value and a covariant metric. Yeah, and each of the diagonal elements of that covariant metric correspond to the variance of the marginal PDF describing a particular component. So element number 1, of the covariant metric is describing the variance of the marginal PDF about x1, in this case about x. And here element number 2, the covariant metric will be talking about component y, and element 3, diagonal element, yeah, that correspond to the heading. And here we have the blue one, the discrepancy, and here the light blue is the correspond to 2 standard deviation, and this seems to be consistent because the error is sort of always inside of these limits. It doesn't need to be exactly or always inside. It could be sometimes it breaks this limit and it's going to be still under plus minus 3 standard deviation. And the probability that it's going to be even worse than that is low, but still is not 0. Okay, this seems to be okay. Everything seems to, depending on the noise we apply, these things are going to be different. So each time that you run this, the noise is going to be a different sequence of values. And this thing will be evolving in a different way, but usually should be respecting these 2 standard deviation. Yeah. All right, this about part A1 of project number 2.